Okay, this is problem number 9. So let's get my stuff ready here. Quite ready. Okay, so number 9, we're just doing antiderivatives. And we use this sign, the symbol, to show the antiderivative. And basically, the antiderivative is the function whose derivative is the original function. So the original function is x to the third root of x. So I need some function. When I take the derivative, I end up with the third root of x without any constants in front of it. Okay, so in this first section, we have page 250, which are a list of the antiderivatives that we know at this point because we know what the derivatives are. So we've taken the things that we know as derivatives and said, okay, we just go backwards in the opposite direction. So what we do is anytime you have a root of any kind, you rewrite it as a fractional exponent. So in this case, third root is x to the 1/3 power. And then you recognize that as a power function. And so we know that the exponent is 1/3. And so when we take the antiderivative or integrate it, we add 1 to it. So we get 4/3. So n plus 1 is 4/3. So the integral of x to the n dx is x to the n plus 1 divided by n plus 1. Again, page 250. So make sure you know where to find that. I'll make a copy of it for the test. But we look through there and we say, oh, there it is, it's power roll, the red thing there. So we rewrite the, we do the antiderivative. So we get x to the 4/3, and we divide by n plus 1. And we add our arbitrary constant c. And instead of leaving 4/3 in the denominator, we multiply by its reciprocal. And I'm just going to leave it as a fractional exponent. I guess theoretically you could write this as the cube root of x to the 4th power. I guess that's the same thing. But I'm happy with just to the 4/3 power. Okay, we're in chapter 4 now. So this is section 1, problem number 10. And what we're doing is completing the table. So it's kind of like when we did stuff where we rewrote an expression when we're taking the derivative of a fraction, basically. So number 10, thing is you've got to rewrite this in terms of this u variable. I think that's, I'm trying to make sure I'm not getting ahead of myself here as far as the rewriting thing. Actually, I'm getting ahead of myself. Okay, so we're just going to rewrite this. Number 10 is the integral of 1 over x squared dx. So just like you had to rewrite the derivative, or rewrite the function to take the derivative when it was in this form, you do the same thing for the integral. So this becomes the integral of x to the minus 2 power dx. And now it becomes a power function integration. So we go to the formula that's in the book for a power formula. And what that says is that the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus this arbitrary constant c. So anyway, that's just using the formula. So in our case, n is equal to -2 to start with, so n plus 1 is equal to -1. So when we do this integral, the original integral, so the integral of x to the minus 2 dx is equal to x to the -1 divided by -1 plus our arbitrary constant c. And then it says simplify, which means that if you have a negative exponent in the numerator, you want to change that to a positive exponent in the denominator, so we get 1 over x to the first power instead of the negative first power. And then we, of course, when you have something in the first power, you just drop that. So that's the answer. And you can always check, if you take the derivative of this expression, you should end up with the original expression. So if you took the derivative of this, let's say f of x is this function, negative 1 over x, which is the same as negative x minus 1. Then you take the derivative, and you would get negative from here, negative sign, negative 1 from the exponent x to the negative 1 minus 1, which would be negative 2. And actually, we can add arbitrary constant c on there as well, but because when you take the derivative of a constant, you get 0. So these cancel out to get positive 1, so you just get x to the minus 2, which is 1 over x squared, which is what we started with. Okay, just check to make sure I had the sound on. Okay, the next problem we're doing is number 12, which is the integral of x times x squared plus 3 dx. So, as you see, we're supposed to rewrite it. And we haven't, if you're watching these after we covered section 5, then there'll be another way of doing this. But at this point in the book, we don't know about how to do that yet. So we would rewrite it just by multiplying everything out. So we'd have x cubed plus 3x times dx. And one of the properties of integration is that you can add the parts of a sum. You can do the integration separately. And finally, and you can skip these steps if you want to, if you understand exactly what's going on, but I factored out a 3 here because this is x to the n where n is 3, and this is x to the n where n is 1. So all we have to do is integrate those separately, get the antiderivative. So the integral of x to the third is we add 1 to the exponent and divide by the new exponent. We have our constant times the integral of x to the first power, which is x to the second power, divided by 2. And we add our arbitrary constant c. You only add 1 arbitrary constant c. We get 1 from each one of these integrals, but we just combine them into 1 arbitrary constant. And that's pretty much it. The only thing we might do is we might just rewrite it as that. So it's 3x squared over 2. And just checking make sure I did this all correctly. Looks correct. Number 13. Okay, so this is one of these rewriting things again. So we have, what is the integral? Actually, we're supposed to call them antiderivatives at this point. So what is the antiderivative of 1 over 2x cubed? So you rewrite the expression, so it becomes 1/2 times x to the minus 3 power dx. So you move that to the numerator, make it negative. Then you integrate, so the integral of, and before we do that, just like with derivatives, the constants can be kind of done separately, just moved outside. So we have x to the minus 3 power dx. So we get 1/2 times the integral or antiderivative of that. And again, this is a power function. So n is equal to -3. What we need here is n plus 1, not n minus 1. So that becomes -2. So we get x to the minus 2 power divided by -2. And we add our arbitrary constant c. So in this case, we have 1/2, and this 2 is in the denominator, so really we're going to multiply 2 times 2, and you're going to have a negative sign, so it'll be negative x to the minus 2 over 4. And then we can simplify by moving x to the minus 2 to the denominator, so we get 1 over 4 x squared plus c. So that is the integral. That's the result. Again, we could take the derivative to check everything out. So you'd have negative 1/4 x to the minus 2 power. So when I take the, let's call that f of x. That's the function after we've done the antiderivative. So you would get negative 1/4. So f prime of x is x to the, well, you have to take the exponent, which is negative 2, times x to the negative 2 minus 1, which is negative 3. And let's put the arbitrary constant on there. So when you take the derivative of the arbitrary constant, you get 0. So you get negative times the negative is a positive. 2 divided by 4 is a half. So you get 1/2, and then x to the minus 3 is the same as 1 over x cubed. So you get 1 over 2x cubed, which is exactly what we started out with. This is problem 14. So we have the integral, or the antiderivative, of the quantity 3x quantity squared dx. So again, if we, using stuff from section 5, we could do this, but at this point we don't know it, so we just multiply it out. So when you square 3x, you have to square both terms. So you get 9x squared. 3 squared is 9, x squared is x, the value x squared is x squared. And what we do is we would factor out a negative, or a 1/9, because that's the denominator. And so we end up with 1 over x squared dx. So now we have a power rule where n, in this case, is actually equal to negative 2. So we have one more step here before we, so we'd say that's x to the negative 2 dx. So n is equal to negative 2, so n plus 1 is equal to negative 1. So we have our constant, and we multiply by the integral of this, which is going to be x to the negative 1 power divided by negative 1, and we add our arbitrary constant c at this point. And to simplify it, we take the negative, put that out with the constant, so we'd have negative 1/9, and then we would change x to the minus 1 power as 1 over x to the positive first power, of course, which is just equal to x. And we probably would combine these two into one fraction, so we get negative 1 over 9x plus c would be the integral. And that's it. If you take the derivative, this is x to the minus 1 power up here, so you'd have negative 1 times x to the minus 2, and negative times negative is positive, and you'd get back to this, and then you could do this factor. You could rewrite that to get back to the original result. This is problem number 17. So we go ahead and break this up into two parts. So we distribute the dx to both terms. Factor out the 2, because that's a constant which we can bring across the integral sign. We have to perform the integration to rewrite the x parts. So the integral of x is x squared over 2, so we get 2 times x squared divided by 2. The second one is 3, and we get the integral of x squared is x cubed. We add 1 to the exponent, divide by the new exponent. These always match up. And then we add arbitrary constant c. And then we simplify. So we just get x squared minus x cubed plus c. And you can see if we take the derivative, we'll get 2x minus 3x squared, which is exactly what we started with. And remember, this integration, we call this an indefinite integral. The result is an equation, and the result with the arbitrary constant c is called the general solution. If we specify some value of x and y, some combination of x and y, where of course this is f of x, well, this is y, then we can find what c is, but in this case we're not doing that. Okay, what's next here? Number 19. So now it says find the indefinite integral and check the results by differentiation, which we've been doing that up to this point. They didn't ask us to do it, but we did it. So we get x cubed plus 2 times dx. Now this, I'm going to write it out, but you could say this is the integral of x cubed dx plus the integral of 2 times dx. And before we'd actually integrate, you would move any constants you have outside the integral. So the 2 comes outside the integral, and you just have the integral of dx. Really have 1 times dx if you want to really get exact about it. So the integral of 1 is x because the derivative of x is 1. So this is a power rule. So what we do is to integrate it, you add 1 to the exponent, divide by the new exponent. The second part, you get 2 times the integral of dx, which is just x, and then you have your arbitrary constant c. So that's the integral. And this is check. So let's call that capital F of x, antiderivative. So if I take the derivative of that, so let's say f, capital F prime of x, then you get the exponent, 4 times x to the 4 minus 1, which is 3, divided by the 4, which comes from here. So this comes from the exponent. This comes from the original expression. Then you have 2 times the derivative of x, which is 1, and you have the derivative of a constant, which is 0. So we'll get x cubed plus 2. That's the derivative, so that checks out. Number 22. So we have the integral, indefinite integral of the square root of x plus 1 divided by 2 times the square root of x, the whole thing times dx. So we have two terms. We're going to do this separately. So we have to multiply dx by both of them. I forgot the first one. Then you're going to rewrite each as a fractional exponent. So this is x to the 1/2 power dx. I'm going to factor out the 2 that's in the denominator. So 1/2 comes out. And what we're left with is the integral of x, 1 over the square root of x, which is going to be x to the minus 1/2 power. Okay, now the constants are outside. We can then add 1. In this case, the first case, n is equal to 1/2. In the second case, n is equal to negative 1/2. So n plus 1 is equal to 3/2, and n plus 1 here is going to be equal to positive 1/2. So the first integral becomes x to the n plus 1 divided by n plus 1. The second term, we have our constant we place out front. Then we have the integral of here, so we get x to the positive 1/2 power divided by 1/2. And then we add arbitrary constant to both terms. One arbitrary constant. Dividing by a fraction, we multiply by the reciprocal. So we'll get 2x to the 3/2 divided by 3. So dividing by 3/2 is the same as multiplying by 2/3. Here, this cancels out with that because 2 times 1/2, we're multiplying the denominators together, is 1. So we just get x to the 1/2 power. And then we add our arbitrary constant c. And the only thing I might do is change this second term to a square root. And that is the antiderivative. It's also the general solution to this equation where you'd say y prime is equal to this, and so the general solution to that differential equation would be that value. This is problem 23. So we have the integral of the cube root of x squared dx. So this is one of these fractional exponent deals. So when you say the cube root of something, that is the same as raising it to the 1/3 power. So basically we have x squared raised to the 1/3 power. And we can go ahead and use the properties of exponents. That means you multiply the exponents here because you're raising this to another power. So 2 times 1/3 becomes x to the 2/3 dx. And the power rule, just like with derivatives, applies for fractional exponents. It doesn't have to be a whole number. So in our case, n would be equal to 2/3. Therefore, n plus 1 is going to be equal to 1 plus 2/3, which is 5/3. So the integral of x to the 2/3 is x to the 5/3 divided by the new exponent, which is 5/3, plus my arbitrary constant. So we'll call that capital F of x. So small f of x is this thing, the original expression. Okay, so now we can check it by taking the derivative. Before we do that, let's clean that up. So dividing by 5/3 is like multiplying by 3/5. All you do is you switch the numerator and the denominator. Okay, so now we take the derivative. So we're going to take f, capital F prime of x. So we get 5/3, the fraction. We take the exponent, 3/5, the exponent, which is 5/3, raised to the 5/3 minus 1 power. The derivative of a constant is 0. So you can see those cancel out. We just get 1, and we get x to the 2/3. 5/3 minus 1 is 2/3. And then you can rewrite it in terms of roots and exponents, so it becomes x squared cube root of x squared, which is what we start out with. Okay, we're on number 25. So we have the integral of 1 over x cubed dx. So we rewrite it as x to the minus 3 power dx. So in this case, n is equal to -3, n plus 1 is equal to -2. So we replace this with the antiderivative, and it's going to be x to the minus 2 divided by -2, plus our arbitrary constant c, and then we simplify it by moving the negative exponent to the denominator and making it positive. This is problem number 28. So we have this one that looks fairly complicated, but because we're dividing it by one single expression, which is x to the fourth, we can take this and break it into three fractions. So we'll get x squared divided by x to the fourth. We will get 2x divided by x to the fourth. And we'll get negative 3 divided by x to the fourth, all times dx. So then you simplify it. So this becomes 1 over x squared, because we cancel out x squared here and reduce this by 2 to do the same thing. The second one becomes 2 divided by x cubed. 4 minus 1 is 3. And this one we don't do anything with because it's already as low as it can go. So those are the three terms. And then we can break it up into three individual integrals. Now I'm going to go ahead and factor out the constants right now, so let's save one step. And same here, negative 3 times the integral of 1 over x to the fourth dx. Now each one of these has to be rewritten in terms of negative exponents. So we get x to the minus 2 dx plus 2 times the integral of x to the minus 3 dx minus 3 times the integral of x to the negative 4 dx. So those are the three terms we have. And so now this is n is equal to negative 2, here n is equal to negative 3, here n is equal to negative 4. So we add 1 to each one of these. And so now we can do the integration using the power rule. So this becomes x to the minus 1 divided by negative 1. The second one, we have our constant times the integral of x to the minus 3. So that becomes x to the minus 2 divided by negative 2 minus 3 times x to the negative 3 divided by negative 3, and then we add one arbitrary constant to the end. And now we simplify. So the first term becomes negative 1 over x. The second term becomes, the 2's cancel out, so we get 1 over x squared. Move this to the denominator. We get negative, 2's cancel out, and then we get negative, actually positive, because we have negative times a negative. 3's become 1. 3 divided by 3 is 1, and we rewrite 1 x to the minus 3 is 1 over x cubed. And that is the answer. Okay, we're on problem number 30 now. So we have the integral of 2t squared minus 1 quantity squared dt. So we don't know how to do this antiderivative as it is. So we would use FOIL to expand this out. So we got 2t squared minus 1 times 2t squared minus 1. So if you multiply that out, you get 4t to the fourth minus 4t squared plus 1, the whole thing times dt. So this times itself is 4t squared. Then you have negative 2t squared, and then another negative 2t squared. That gives you negative 4t squared, and negative 1 times negative 1 is positive 1. And we could break that up into three integrals, and we'll factor out the constant. And the integral of dt is just t. So we get 4, and t to the fourth, we add 1 to the exponent, divide by the new exponent. Then we have negative 4 from here, times the integral of that, add 1 to the exponent, divide by the new exponent. And the integral of dt is just t. and we add our arbitrary constant. So we can simplify this, not very much. We just basically get rid of those little dots to make it look a little neater. And there we go. Number 33. We actually just did this in the previous problem. The integral of dx is just x plus arbitrary constant c. So all we really have is 1 times dx. And the integral of a constant is just the constant times x. In this case, the constant is 1. So we just end up with x. Okay, we're on problem 35, which is a trig function problem. So nothing's any different. We just have to use the antiderivatives of trig functions instead of antiderivatives of power functions. So we have the sum of 2 terms. So the integral of a sum is the sum of the integrals, just like the derivative of a sum is the sum of the derivatives. So we can distribute the dx to both terms. And then we can take the constants outside. And then these are in the table. So just like integrals, derivatives, we get it into a form that matches up with the expression in the book. So if you look at the integral of the sine, it's negative the cosine. And if you look at the integral of the cosine, it's positive the sine. And again, we add an arbitrary constant. You could get 2 arbitrary constants from each one of these. Well, an arbitrary constant from each one of these terms. But because they're both arbitrary constants, you add them together and you get another arbitrary constant. So whenever we integrate, even if it's multiple parts, if it's 5 parts, we'd still only have 1 arbitrary constant. We just have to add that at the end. Okay, so what do we get? We get negative 2 cosine of x plus 3 times the sine of x plus c, and we'll call that capital F of x. So to check this, we take the derivative. So we get negative 2 times the derivative of the cosine, which is negative the sine. Then we get 3 times the derivative of the sine, which is the cosine. And we get the derivative of a constant, which is 0. So negative times a negative is positive. So we get positive 2 times the sine of x plus 3 cosine of x. And you can see that's what we started out with. Number 36. So 36 consists of 2 terms, so we do them separately. One involves a trig function, and one is just a polynomial. So we break this up into the integral of t squared times dt, and then we have a negative sign, so I'm going to bring that out front, the integral of sine of t dt. So here n is equal to 2, n plus 1 is 3, so we get t cubed over 3. The integral of the sine, if you go into the book, you'll find out it's negative the cosine. And then we add our arbitrary constant c. So the last thing we need to do is just simplify by removing the 2 negatives and just making it positive. And that is the answer. Problem 38. So we have the integral of theta squared plus secant squared of theta all times d theta. So as before, we have two terms that are added together, so we can do the integral of each one separately. The sum of the integral of a sum is the sum of the integrals. The variable is theta, so it's just like x, except we're using theta, so there's no big deal here. First one is a polynomial, so n is equal to 2, n plus 1 equals 3. Here, we have, if we go to page 250, we'll find out that the antiderivative of the secant squared of x dx is the tangent, so all we do is say it's tangent of theta instead. So the first term becomes theta cubed over 3, and the second term becomes tangent of theta. And then we add an arbitrary constant c. And that is the answer. So you notice every time we've done this, we've always ended up with something that we can look into the table on page 250 and recognize it as one of those. And basically that's what we're going to have to do. We're going to have antiderivatives. We're going to have a more complicated list when we get to the end of chapter 5, but right now we have a limited list. Okay, let's do another trig problem. So we get the integral of the secant of y times the tangent of y minus the secant of y times dy. Now we're going to multiply this out. So you get the secant of y tangent of y minus the secant of y squared, and all of that multiplied by dy. And then you can distribute the dy, so we end up with two integrals. The secant of y tangent of y dy minus the integral of the secant squared of y dy. So all we're doing is just doing the algebra. We haven't done any integrations yet. So now we go to the table, which is on page 250. And so we go over to the right column, and we look down the table and see secant squared. The integral of secant squared is the tangent. So instead of, we can substitute in for this, we can put the tangent of y. And the integral of the secant tangent, we go down one more step and we get the secant. So the first one is the secant of y. And we get two arbitrary constants, but we combine those into one arbitrary constant. So that's the answer. So let's call that f of x is that. So to check it, we just take the derivative of each one of these. So we take f, capital F prime of x. Now we go to the left-hand column on page 250, and we say, okay, what's the derivative of the secant of y? And we see it's the secant times the tangent. So we get secant of y tangent of y. The derivative of the tangent is the secant squared. The derivative of constant is 0. And then we can factor out the secant, which is what they did here. So you get the secant of y times the tangent of y minus secant of y. And we're back to where we started again. This is problem 58, section 1. So let me turn the page so I actually have it. So, okay. So this one's solving the differential equation. So what we have is f prime of s is equal to 6s minus 8s cubed. And we have this, which is called the initial condition, or at least it's a condition. Because if we integrate this, basically what we do is we say the solution to this differential equation, which is f of s, is the integral of f prime of s times ds. So since these are opposite of each other, you know, the integral of the derivative is the derivative of the integral. We can go back and forth. So what you can say is, you know, f prime of s. The other way of saying this is f prime of s is the derivative with respect to s of f of s. Or we can go the other direction and say that the function is equal to the integral of f prime of s ds. So to be able to solve the differential equation, all we have to do is just plug in f prime of s into this equation. So we can say the function is the integral of 6s minus 8s cubed all times ds. So just for f prime of s, I've put in the expression, and then I multiplied by ds. These always have to match up. This variable s has to match it. ds, if it's x, it has to be dx. Now when we integrate this, take the antiderivative of this expression, we're going to end up with an arbitrary constant, and that's what this is for, is to give a value to the arbitrary constant. Okay, so solving this differential equation is integrating that, and what we'll get is 6, the constant, times s squared, because you add 1 to the exponent and you divide by the new exponent. Do the same thing for the second one. We have the constant, we add 1 to the exponent, we divide by the new exponent, and we have our arbitrary constant c. Let's clean it up before we apply what we would call the initial condition. So you have 3s squared minus 2s to the fourth plus c. So to find c, we would say apply the initial condition. A lot of times the initial condition is when, in this case, s would be 0, but it doesn't necessarily have to be. So, okay, so what we do is we say f, we know that f of 2 equals 3. So 3 is the value of the function. And then you plug 2 into this expression. So you say 3 times 2 squared minus 2 times 2 to the fourth plus c. What that means is when I plug in 2, I want to end up with 3 on the left-hand side. So I have to figure out what c has to be for that to happen. So I just solve for c, basically. So you get 3, which is the left-hand side. We have 3 times 4, which is 12. We have 2 to the fourth power, which is 16. So we get 2 times 16, which is 32. And then we add c. So let's go ahead and do that subtraction, which would be negative 20. And then you add 20 to both sides. So you get c is 23 is equal to c, or c is equal to 23. So our solution is going to be 3s squared minus 2s to the fourth plus 23. Now you can check that by just plugging in f of 2 now. So that means plug 2 into here. So you get 2 squared minus 2 times 2 to the fourth plus 23. So that's 3 times 4 is 12 minus 32 plus 23. And if you plug that into your calculator, you should get 3. So 12 minus 32 plus 23 is 3. So that works. Okay, this is the last problem in section 1. It's a word problem. So we just have to read the problem and then see if we can come up with what it says. An evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during those 6 years is approximated by dHdt. So that's growth rate. So when you use the word rate, that means that it's some function of time. There's a change. So it's equal to 1.5 t plus 5, where t is the time in years, h is the height in centimeters. The seedlings are 12 centimeters when planted, so when t equals 0, h equals 12. So that's what we call the initial condition. That's the value of the function at t equals 0. So this will help us find the arbitrary constant. And what we're looking for is the height as a function of time. So the height as a function of time would be h prime of t times the integral of h prime of t dt. You could say that. You could say it's the integral of dh dt times dt. So dh dt is this. This is also h prime of t. They're just different ways of representing the derivative. So all we have to do is to find the height as a function of time is to integrate this thing. 1.5t plus 5, the whole thing times dt. So we integrate each part. The integral of 1.5t is 1.5. This is raised to the first power, so we add 1, so you get t squared. You divide by the new exponent, which is 2. So that's that part. The second part is the integral of 5 dt. So you have 5 times the integral of dt, which is just t. And then you have your arbitrary constant, which we'll find out what that is based on this initial condition. So what are we going to do here? We can kind of simplify this. If you multiply by 2, both the numerator and the denominator, you get 3t squared over 4. 1.5 times 2 is 3. 1.5 times 2 is 3. 2 times 2 is 4. I just did that to get a nice whole number fraction. Okay, so we call this the general solution because this applies, if this differential equation applies for all trees, for this particular tree where the initial height is 12, then we can plug that in and get this particular solution, but the general solution includes the arbitrary constant. So now we're going to apply the initial condition. So the initial condition is that basically h of 0, the height at t equals 0, is equal to 12, and that's equal to 3t squared over 4 plus, well, actually we're going to stick t equals 0 in there, so you get 3 times h of 0 means at t equals 0, so you put 0 in there. And you see the two terms are going to go to 0. So the only thing that's left is the arbitrary constant. So you get 12 is equal to c, c is equal to 12. So that, our particular solution for the case where the initial height is 12, is h of t equals 3t squared over 4 plus 5t plus c, which in this case is 12.